So now that we've talked about simplifying radicals with negatives under the square root, I need to say one more thing about that before we go on. Okay, once we get used to seeing this, a lot of students want to just put an I anytime they see a negative number. Okay, however, don't forget that the cube root of -8 is still -2. Okay, there's no I involved in the cube root of anything negative. Also, a fourth root of a negative number, we're still going to stop and say not a real number. Okay, there are ways of writing it in terms of I, but I is specific to the square root. We don't just put an I anywhere we see a negative number under a root. Again, odd roots, we're allowed to be negative to begin with. Even roots, those are not real numbers, and that's still the truth up here. This is not a real number. But we have a definition now to deal with square roots of negatives. But the door's really only been open to that one extra case. Okay, all the rest of them from our section still work the way they did before. Okay. So when we talk about complex numbers, a complex number is a number of the form a plus bi, where a and b can be any real number. So complex numbers might look like 12 minus 7i. They might look like 1/2 plus the square root of 10 times I. It is possible that one of the parts is 0. So the number 5 is also a complex number because it can be thought of as 5 plus 0i. Or just the number 6i is complex because the real part is 0. We can think of it as 0 plus 6i. In a, the real part of the number is called the real part of the number. And b, the coefficient on the I is called the imaginary part. So -7, square root of 10, 0, 6. When we do arithmetic with complex numbers, it would work the way your intuition would hopefully lead you to believe it should work. Anytime we add anything or subtract anything in algebra class, we know we can only combine terms together if they are what? Like terms. So the terms here that are alike, 3 and the 9 are alike. The 4i and the -i are alike. So when we add these two complex numbers together, we get 12 plus 3i. If instead of addition, we're asked to subtract those two numbers, we know that anytime we subtract an expression, that negative sign does not just hook onto the first number or term, it has to hook onto all of them. Meaning I need to distribute that negative sign to every piece involved. So just like we would with an x or a y, or a square root of 7 and square root of 5 like we did in the last section. Okay, once we distribute, then we combine our like terms. If we multiply these two complex numbers, then when we start at our desk, we're going to FOIL. We're going to distribute and expand this out. So our first terms, our outside terms, our inside terms, and our last terms. And like we're used to with our x's and y's, oftentimes those outer and inner terms are like terms and we can put them together. -3i plus 36i is a positive 33i. But also understand when we're simplifying complex numbers, we always want to leave our final answer looking like a plus bi, where a and b are the real numbers and there's no I squareds and there's no I cubes, there's no 1 over i's in our problem. So if we come back up here, and we saw this when we were simplifying our radicals earlier on, we said, well, we know that I squared is equal to -1. So if we have -4i squared, that's the same as -4 times -1. And -4 times -1 is +4. After we distribute, when we go to combine like terms, our outer and inner terms are usually our like terms like they always have been. But now our first and our last terms also are alike if we understand the substitution here that we need to do. Okay, so it looks like my eyes are saying one thing and doing another. Okay. So 27 plus 4 is 31. My brain was already seeing the 33i, and so I was writing that instead of what I needed to be. Okay, that product is 31 plus 33i. When we do division with complex numbers, okay, division is not the same as long division. Okay, that's not what we're looking at here, but it's more like rationalizing the denominator, like we did at the end of our arithmetic part of the radicals, which means I need to be able to write this fraction in an equivalent form, but I'm not allowed to leave any i's on the bottom of a fraction. I know no irrational numbers are allowed to be there. I had to get rid of all square roots, and so that includes my i's. We also saw an example where we had a sum or a difference of radicals there in the bottom, and so that required a special trick or a special expression that we used to multiply to get that, in this case, the I off the bottom. Okay, the word we used to describe that was conjugate. Remember, when we create or work with the conjugate of an expression, in this case our 9 and our I, they don't change at all. Okay, 9 stays 9 and I stays I. But it's the sign in between them that switches. So the minus sign turns into a plus. Had it been a plus here, we would have used a minus. Now we FOIL on the top. We'll go, and then we'll clean it up. We'll go back later and FOIL on the bottom and clean that up. Just let me keep going across the top. 3 plus 36 is 39i. A positive 4i squared is a positive 4 times a -1, which is a -4. So 27 minus 4 is 23. Here's the top of our fraction. On the bottom, our first, our outside, our inside, our last. And remember, the reason we pick the conjugate is because this happens. It gets rid of that piece that we don't like anymore. And the opposite here of -1 is +1, which means the number on the bottom is a +82. When we multiply a complex number by its conjugate, we always get a positive number, and it's always a real number. Okay, because this minus a negative is going to be plus a positive. Now the last step is a cosmetic step, but it's still a required step if you want full credit on your homework quiz or test. We need to split the fraction into 2 pieces, and then if possible, we're going to reduce to lowest terms, each of the fractions individually. 23, and 82 don't have any factors in common, so they don't reduce any farther. So this is where I stop with this. Okay, so at your desk, go ahead and pause the video and add, subtract, multiply, and divide this pair of complex numbers for me, please. When you're ready to see the answers, turn it back on, and we'll see how you did. All right, so for the first one, and my video is about to get long, so I'm going to wrap up my my talking and make it kind of fast. But we add our like terms and get 11 plus 5i. Here on the second one, when I distribute the negative sign, 5 minus 6 is negative 1. 2i minus 3i is negative 1i. Next, we're going to FOIL. First, outside, inside, last. And because 6i squared is the same as 6 times negative 1, or negative 6, we get 24 for the real part, plus 27i for the imaginary part. When we multiply top and bottom of this fraction times the conjugate, on the bottom, the i's go away. We get positive 9 here from minus 9i squared, which is 45. Here we get 36. This becomes a positive 6 minus 3i. When we split the fractions into two pieces, notice that I can reduce each of these this time. I can take a 9 out of the top and the bottom to get 4/5. I can take a 3 out of the top and bottom to get 1/15. Now notice how I set the I up here on top with the 3. That's okay with me if you put it on top here. Your other option is to put it out to the side. But if you write it out to the side, I need you to be very clear that it's out there to the side. I'm going to do that. Okay. Because sometimes people will write things like this. And then that makes the I look like it's where? Okay, on the bottom. I don't want it on the bottom. I don't want it to even appear like I might think it's on the bottom. So if you're going to write it beside, make sure it's very clearly beside. Or if you don't want to mess with that, you're afraid you might get sloppy, just leave it on top with whatever number's on top. That's acceptable. But the fraction does have to be split into two pieces and reduced all the way to lowest terms. So here are your 4 answers in the boxes that would be accepted for full credit.